It's a pleasure to be back here in Galveston. I actually did a sabbatical leave way back in 1987. I barely recognized the campus, but it's fun to be back. Thinking about pulling together a seminar about protein to come to Galveston was always something that makes me scratch my head, sort of come back to an area where people think about protein all the time. So since I have an emeritus title, I thought it'd be good to sort of philosophize a little. You get that right once you retire, don't you? So I think I'm going to sort of overview our research and maybe try and put a different perspective as we think about protein. So one of the things that's been happening is we're thinking a lot different about adult protein requirement. Protein in general has always been about about growth, and now we're focusing more on the healthy aging aspects and the needs for adults, and we're beginning to learn that there's some pretty different thinking. I think one of the things as we start thinking about protein is trying to decide how we should define it. It's been related to growth and it's been related to nitrogen balance, and as we start talking about adults, we need to frame the question differently. And so one of the things I'm going to sort of try and address is what are the units we should talk about when we talk about protein needs, and what are the measurements? One of the problems we have right now in nutrition looking at protein is what I would call trial and error nutrition. It's kind of like my protein level is better than your protein level. This is high, that's low, what's high, what's real high. We don't really have any criteria for defining it. And so how should we go about trying to define what level's enough? So sort of as an outline, I'm going to sort of review some of that thinking, what measurements should we use. Then I'm going to talk about amino acids as metabolic signals. I think that we need to move toward looking at amino acids for other purposes. And one of the ones that we've been learning a lot about is metabolic signals. And as Doug mentioned, we've done a lot of work with leucine. So I'm going to concentrate on leucine as a signal and both initiation and some new work that we've been doing with energy regulation related to elongation. As you probably all know, the protein requirement is set at 0.8 grams per kg. That is the RDA, the recommended dietary allowance, and that is viewed by many as being too low. And a lot of people are debating about what level. Is it 0.9, 1.0, 1.1? I think that's really the wrong discussion. The RDA is defined to be the minimum to prevent deficiencies, and that's what it does. We don't have kwashiorkor, we don't have Erasmus in the US. It prevents deficiencies. A lot of people argue about should it be expressed as per kg of ideal weight, per kg of current weight. I think, again, when we talk about adults, it's the wrong question. We need to define it in different ways. And I think the more important questions is we need to address the difference between a minimum RDA and a more optimum metabolic target. What would that mean? We need to recognize that there are differences in protein needs for children, where growth and hormones are driving the issue, versus adults, where maintaining long-term health and aging is a target. And as we do that, the question becomes really quantity and quality of protein at individual meals. Sort of in the aspect of defining protein, how we talk about it, one of the things that nutrition has always done is talk about macronutrients as percent of calories. And one of the things that, if nothing else, you walk away with, you should recognize that percent of calories makes absolutely no sense for protein. Okay? There's absolutely no data to relate protein to percent of calories unless you think about it as an inverse relationship. If you're doing weight loss and you're restricting calories, your protein needs are the same, so they automatically become a higher percent of calories. Okay? But there's absolutely no physiological reason to relate it to percent of calories. If we relate it to grams per kg, the traditional measurement, what that does is say that basically it's the freshman nutrition course that says protein supplies amino acids as building blocks for protein. It's a substrate concept. We're basically saying we need a certain amount of substrate to maintain a certain amount of lean body mass. I would argue that that is a concept of minimum needs and not a metabolic concept of optimum. And so again, I question whether that's a useful criteria for adults. The one that I'm going to focus on is the metabolic signaling criteria, and that really ends up being grams per meal. And I'm going to try and make a case that that's really the way we should think about protein for adults. You're probably familiar with the dietary reference intakes, the DRIs, so that just gives us sort of a frame of reference. RDAs at the minimum level down here at 0.8 grams, and we know that there is a safe level above that that's quite a bit higher. And where that is we don't really know for an upper limit, a UL, but we know it's somewhere above 2.5. It could be 3, it could be 3.5. And then, again, you have to separate out experiments that do acute doses. If you take somebody who's on a very low protein diet and you give them 200-gram meal, obviously they're going to have some nitrogen problems. But if you let them adapt to it over a few weeks, our ability to handle protein is almost unlimited. So at this point, it's a very high number, and just taking in 2.5 grams per kg is a massive undertaking. So we have a huge safety range. Minimum versus optimum. As we talk about the RDA and the minimum, the traditional concept is about the 9 essential amino acids, and this is that concept of substrate and building blocks of new protein. Traditionally, we talk about limiting amino acids. Which ones are most limiting in food products? And lysine, methionine, threonine become the topics because they're the ones that are most limiting in the RDA sense of building blocks. We have to have enough of those, and if they're limiting in something like soy or wheat or something like that, those proteins are considered incomplete. And so that's sort of the important aspect of minimum. But as we get higher, these 3 amino acids have very limited metabolic roles. And as we start talking about optimums, these aren't the relevant amino acids. These aren't the relevant essential ones. As we think about the issue of protein needs, one of the other things to keep in mind is the historical thinking about protein is always related to efficiency of use. There isn't any other nutrient that we apply efficiency to, only protein. And so if you think about a concept of efficiency, nitrogen balance, basically as you titrate protein in, you go from 0 intake, higher levels, you'll get to a point where protein, nitrogen in and out of the body becomes balanced approximately. We call that the requirement. We actually use the break point in that it never really goes to 0. The more protein you take in, the more tissue you will deposit, primarily liver and kidney and gut, but basically it stays positive. It never really flattens out. I mean, it changes slope, but it doesn't flatten out. Even more important than nitrogen balance and how it misleads us, though, is the concept of amino acid oxidation. We believe, and there's concepts of oxidation out there, that you should have the least amount of amino acids being oxidized, kind of a cost thing or something. And that once you get plasma amino acids will stay flat, and once they break and start up, that's excess protein, that is inefficient use. And my argument is going to be that all of the metabolic outcomes that we want to stimulate actually require increasing plasma levels. And if you don't increase plasma levels and stimulate oxidation, you won't get these effects. So we have to walk away from concepts of efficiency as being important for protein nutrition. Going back sort of historically, where'd that come from? Animal science is really the history and the traditional the origins of a lot of our nutrition thinking. And so from our traditional view in animal sciences, the targets were always growth. Animal science is about production. We're trying to grow the largest animal in the shortest period of time. So most of our thinking about protein comes from weight gain. We have a lot of knowledge about children and protein needs, etc. It's all about efficiency. And if you think about it, sorry, I lapped a little bit here, from an animal science standpoint, again, it's cost benefit. We want to get the largest size for the least cost. In human nutrition, that's probably not a particularly good thought, right? I think in the South you call them buffets, right? Largest size for the least cost. Anyway, as you look at how farmers and agriculture looked at that, it was a very high carb diet with very low protein. You want maximum amount of energy intake with the least amount of protein. It's a cost-benefit relationship. Okay. My father taught me, I grew up on a farm in central Illinois, and he said if you want to fatten a pig for market, feed it lots of grain with very low protein, and you can market a 220-pound pig in 5 months. We also tried that in human nutrition. We call it the food guide pyramid. What that says is eat the least amount of protein and the maximum amount of grains, right? And we sort of all know how that worked out. If you look at, anybody remember when the food guide pyramid was introduced? 1988. So when you put it on that framework there, what you see is basically in 1985 we had very little obesity in the US. 1990 it's clearly changing, and by 95 we've got a serious problem going on. USDA finally recognized all of that, and in the 2010 Dietary Guidelines made a major shift. So we shifted away from the philosophy that the first thing in nutrition is avoid fat, limit animal products, and eat lots of grains, and we totally dropped the pyramid unceremoniously and went to a plate look. And so what you see now is we're emphasizing vegetables, protein groups, dairy and protein, and we've minimized that grain category. What they found was that what had happened after 1985 was the American public had increased caloric consumption by about 325 calories per day, and it all had come from grain categories. Breads, pastas, pizzas, desserts, cereals, granola bars, and sweetened, sugar-sweetened beverages that came from corn products. So what we've done is minimize the grain category, and we've emphasized protein and vegetables as we remodel our dietary guidelines. About the same time, a number of people, Bob Wolf included, who started emphasizing that for adult health, one of the key things is fragility, it's muscle integrity, it's maintaining muscle health for a long term, and that started shifting us away from general thoughts about nitrogen balance to more targeted metabolic concepts. So let's go back then to the amino acid case and start thinking about, instead of general protein and overall nitrogen balance and thinking about just essential amino acids as building blocks, let's think about specific roles of amino acids. And there are lots of them, just a listing here. I won't spend time on this, but I'm going to emphasize the aspect of leucine, but we can make some arguments for each of this. But let's shift over and think about it as a signaling aspect. So we now know that there are a lot of amino acids that have signaling roles. So arginine is a production of nitric oxide. It's a signaling element. Tryptophan for serotonin, or tyrosine for dopamine. Phenylalanine for CCK production, or leucine for GLP-1. And the one we're going to focus on more is leucine and mTOR signaling. What we now know about all of these is they relate to the amount of the amino acid in the tissue, the intracellular concentration. And if you want these mechanisms to function, you have to function with them increasing. They function by their concentration in the blood or the tissues. And so you can get along with minimum levels, minimum RDA levels of protein, but you minimize all of these roles. And so you see people supplementing arginine. You see, the reason is the protein's too low in the first place. So if we want these roles to function, then we have to change the blood levels. We challenge that efficiency oxidation concept. Why is leucine so unusual? Leucine is one of the 3 branch-chain amino acids, and these 3 make up 25% of total protein. They're present in very large amounts. But what makes them really unusual is that most amino acids are metabolized in the liver and the gut. And so on first pass through the liver and gut, the body eliminates 50%, oxidizes 50% of amino acids when you eat them. 50% never get to the blood. And in some cases, like threonine, 75% is extracted on the first pass. Glutamine, 99% is extracted before it gets out of the gut. So most of them are cleared, but the one oddity is the branch-chain amino acids, where the first enzyme, the transaminase, is not present in the liver, and so basically they appear in the blood in exact proportion to what you ate them. And what is important about that is muscle has learned to recognize that as a signal. It's a signal of you eating. It's a signal that the substrate level, that the amino acids that are coming in are now balanced. Why did it pick leucine and branch chain? I don't have a foggiest idea. But it evolved that we have a metabolism that assures that these are delivered to muscle in proportion to the meal. And that's a real key. And one of the other things that we now know is that as I talk about signaling, what we also know is that the oxidation triggers at the same time. And so we think about amino acid oxidation, they have the same KMs. Basically, when it triggers the signal, it also triggers the degradation system to get rid of them at the same time. So what that means is the signal never becomes insensitive. It eliminates it after the meal, and so you get a pulsatile recovery. Again, spirit of philosophy, I'm going to go back to a couple of early studies. So this 1984, this was one of the first studies back in the leucine era, and we were thinking about some of this research. And there's sort of 3 points I'd like to make about this really early study. And this was back before we had lots of great isotopes. We weren't really doing infusions. We weren't doing stable isotopes. This was back in the old days. And this is actually an in vitro system. So back in those days, Fred Goldberg and Marcy Boos and others were looking at leucine and Al Harper, and we were looking at leucine and metabolism. And what we realized is it had some unique effects on protein synthesis, but they were all doing isolated diaphragms and heart perfusions and hind limb perfusion. Nobody had actually looked at skeletal muscle. So this is actually the first study that ever published that actually looked at leucine and skeletal muscle protein synthesis. So I like to think that was first, but anyway. A couple of things about it. So when we do these studies, you take out a muscle and you do it in isolate, you do it in Erlenmeyer, and you basically put the medium in. A couple of things that we learned about it. One is we learned something about the concentration. To get a leucine effect, you have to go to around 5 millimolar. So the take-home message of that is that you need to go from a fasted level to 2 to 3-fold above that before you'll get an effect. So there's that oxidation question again. If you don't increase the intercellular and plasma levels, you won't get an effect. And the other point is you're going from a negative, fasted, you're going from a catabolic condition to a positive. If you're already in a positive and putting on more leucine on top of it, you'll get no more effect. It's the transition that's a key. What we found was that when you take a muscle out and do in vitro studies, it's immediately dropped to catabolic. It's immediately, so even though it's a fed animal, it's only protein synthesis is 25% of normal. Put leucine on top of it and you'll recover it. You'll get a 50% increase. Huge response. If you look at the same and do a 24-hour fasted animal and add leucine on top, you'll get a similar 60% increase. So both of them produce an anabolic response. But what we also did that was a big learning for us is that when you went out to 72 hours, you started losing the effect. So what this told us at that point was it's an anabolic, it's an effect on initiation. Once you start getting into the catabolic period where the machinery is going apart, where you're decreasing ribosome aggregation, where you're decreasing the amount of ribosomes in a catabolic condition, you can't then put leucine on and expect an effect. There were a lot of studies, Dwight Matthews and others did, where they tried to infuse leucine on top of a surgical situation where the person had been hospitalized for 3, 4, 5 days, maybe a week, and then tried to add leucine, where you're already catabolic. The process is lost. It's too late. Okay? You can't recover because you've already changed to something else. So that was the second. First is concentration. The second is that it's an initiation effect. And the third we learned is that it's different from muscle to muscle. Now, I'll come back to this point later. When we looked at the EDL, so the soleus is a red postural muscle, very high mitochondrial content. The EDL is an extremely white propulsion muscle, very low mitochondrial. And you'll see that it's much, much less effect. And so as you're doing studies, you need to realize there's a fiber type difference, and mitochondria make a difference, and I'm going to come back to that. So when we're doing animal studies, they are willing to give us the whole muscle. When you're doing biopsy studies, you have to be sensitive to what you got. Jumping ahead to 98, we sort of had the target. We were pretty sure it was initiation. It took about a dozen more years before the technology caught up that we could do the westerns, we could do the phosphorylation. So I want to show a couple of studies and, again, sort of historical effects or context here. First of all, this study was kind of fun, and I think just looking at the author list is kind of fun at this point. So Tracy Gausch, now Tracy Anthony, married to Josh Anthony, the second author, two of the leading people in the protein. Scott Kimball at Penn State, Greg Paul at Soleil, some of you are knowing, another student in my lab, myself, and Jim Jefferson. So basically, we brought that team together sort of in that context. Back in the mid-90s, everybody looking at initiation was using the liver. It was easier to use. Muscle was way too difficult for these kind of techniques. The Jefferson lab had all the antibodies for these, so they weren't commercially available. So they had the antibodies. So I called up, I'd known Jim, and I called him up and invited him out. So they were all studying EIF2 initiation factor 2 and 2B, and that initiation factor is energy dependent. And so everybody at that point thought it was all related to energy because they were studying liver. What we realized and what we had done is looked at some of those factors, and we realized that in muscle, the EIF2B part of the equation was fourfold higher than in liver and could never be limiting. So we realized it wasn't 2, that it had to be something else, and we started focusing on EIF4. So we brought Jim out and sort of posed our hypothesis, and we also had developed the concept of doing exercise. We wanted something that would make the transition for protein metabolism very quickly. We didn't want it to go catabolic, so we couldn't recover it. So what we found is we could do endurance exercise, exhaustive exercise, and we can make it go catabolic in an hour and a half or 2, and then look at recovery where everything was still intact. And so we developed the exercise protocol for that. And sort of debating the 4E versus 2B question, Tracy and Josh still joke that we brought Jefferson out, and the arrangement was Tracy and Josh would go back to his lab to actually do the measurements. And when they went back out there, Jim told them, he says, you know, it's a cute theory, but your advisor's all wrong. And they proceeded to do a decade's worth of research on this very topic and 150 publications, but maybe not. Anyway, history, I reminisce. From that, we went on then to do specifically leucine studies, and I'll talk about that one for a second. So here's Tracy and Josh again. And this is a model that we have used in a lot of leucine studies, so I'll just highlight it. So we did, just for ease of numbers, 100% is our control. We did a 2-hour, fairly exhaustive treadmill running with rats, 75%, so we dropped it 25%. And then we started to look at recovery. So we did our sort of Gatorade experiment. We gave a fairly large dose of carbohydrates for recovery, and you see glycogen recovery, but the longer you go, you see it's actually protein synthesis still going down. Carbohydrates, insulin had no effect on recovery of muscle protein synthesis. We then did all sorts of things. The first study, we used Ensure, we used complete meal replacements, we used protein, then we started fractionating the protein. We realized it was a protein fraction. We went to amino acids, and eventually we got down to realize that the effect was really due to leucine. We could give a dose of leucine basically immediately after the exercise, and we could get full recovery in less than 30 minutes. Okay? And then we looked at the recovery with leucine and carb, and we got a little bit different, a little bit higher, but not statistically different. These 3 experimental models then became really the standard for all of the leucine. So this is a high carbohydrate meal level that's an oral gavage. This is leucine at the equivalent of the full daily dose of leucine based on the RDA. So it's a big dose, and then this is the combination. So that's a model you're going to see again later. So we've gone on, we know a lot now about leucine, mTOR reactions. We know how it stimulates protein synthesis. We know the interaction with insulin. I'm going to talk about that in a second. I just want to highlight one other thing I'm going to come back to in a few minutes. We also know there's a relationship to energy and particularly AMP kinase, which is an energy sensor. So just to position that here, I'm going to come back to that later. So we know a lot more about initiation now. We've pretty well evolved to where we understand all of the initiation factors, how they interact, how they build the scaffolding for triggering the initiation process and starting protein synthesis. So when you're in a catabolic condition and you want to recover and stimulate protein synthesis, this is the trigger. If you don't trigger it, it doesn't matter how many amino acids you give, doesn't matter how much carbohydrate you give, it won't happen. So this is a trigger, it's a threshold. Just to simplify that picture and make a couple of points, so this is sort of our anabolic drive for protein synthesis in muscle, and it's a combination of insulin and leucine. And if you think from a dietary standpoint, the muscle now is sensing two things. It's sensing energy and it's sensing protein. And it wants to sense those two to trigger this process, protein synthesis. If it doesn't know it has adequate energy and it doesn't know it has adequate protein, it's not going to trigger. When we're young, this equation is dominated by the hormone side. Insulin, IGF-1, growth hormone dominate the trigger. And so you can give protein in small doses, or you can give it in large meal, small meal, wherever you want, and individuals will grow. Lots of childhood nutrition on that. So grams per kg makes a lot of sense for children. Once you stop growing, insulin ceases to be very effective as a hormone. Insulin, first and foremost, is a growth hormone. Secondarily, it does some glucose things, but actually kind of trivial to tell you the truth. It's really more of a safeguard against excess. It's not really regulatory, as most people think. So basically, insulin is a triggering mechanism, but as we get older, that doesn't do much. It just sort of needs to be there in a permissive role. Leucine and protein, then, the quality of the diet become the dominant influences. And so as we get older, as we look at aging in the long term, now the quality of the diet becomes much more important in how we distribute it. So as we looked at this leucine effect, what we've been able to do is basically look at muscle protein synthesis and look at leucine levels at different levels, grams, so in a human diet. And we've basically been able to realize that this is a threshold response. If you put leucine into a meal up to about 2 grams, you'll get 0 response in muscle. It has absolutely no effect at all. But once you cross that level and you get up to 2.5, 3, 3.5, what you get is a dramatic threshold triggering of protein synthesis. We trigger that initiation. We assemble the ribosome, we assemble the mRNA when we trigger protein synthesis. It's a threshold response. And when you give a lot more, you don't get much more effect. It's not additive. Once you trigger it, it's now triggered. And it will stay triggered until until you run out of nutrients then. So basically, it may increase a little, and some bodybuilders are interested in taking 4.5 grams. But for the most part, if we're working with adults or aging or people in weight loss, what we want to do is trigger it for the fewest calories. If we add protein across that at the bottom, basically we can line up protein levels. So leucine makes up about 8% of proteins, and so 3 grams of leucine ends up giving us that 30 grams of protein, which is the number we've used in all of our studies. And so when we talk about 30 grams of protein distributed for adults and aging, this is one of the places it comes from, and it's a mechanistic way to justify it. Borrowing a slide from Doug and Ben here, basically one of the things we know from NHANES data is basically that most Americans eat 65% of their protein in one meal. And so now we start thinking about this triggering mechanism, and what we see is that the other 2 meals are below the leucine threshold to actually give you any effect. So what we have is 1 meal that exceeds our needs and 2 meals that don't meet the threshold. And so now we're starting to talk about the redistribution. Why does that make any difference? Basically, after a meal, we know that there's about a 3-hour effect of protein synthesis. So you get an anabolic response that lasts about 3 hours. And so triggering here with the meal, we go up, we peak at about 90 minutes. By about 180, it's come back down to baseline. So keep those three numbers in mind, the 3 time points, because I'm going to use those again, but that's kind of the pattern. So if we look at overall protein balance, what you see is that most adults in the US go through the day, sleep time, all day long in a catabolic state. They never have enough protein to trigger it. So basically they wake up in the morning, they're in a catabolic state, they're breaking down tissues, and they stay that way till dinner, at which point they get a 3-hour anabolic period. So we're 3 hours anabolic and 21 hours catabolic. In conditions such as weight loss, where you're automatically catabolic, you're losing weight, that's a serious problem. Bed rest, working with NASA, space flight, those are serious problems if you stay catabolic because you're already catabolic. And I think in sarcopenia and long-term, that's a big issue also. So what we're wanting is a more patterned effect where we get multiple meals, probably at least 3. And we've used this pattern in a lot of our weight loss studies. So I just I'm going to talk about some animal studies, but I just wanted to highlight 3 human studies. So this is a series of 3 weight loss studies that we published, going from very short-term, highly controlled dietary things where we basically established the meal threshold concept. 30 grams, 3 grams of leucine, 30 grams of protein. And then the second one that I'm going to talk about is diet and exercise. And the third one is a year-long multi-center weight loss study. All of those, what we show is that we can modify body composition. So I want to talk about this one for a second. It feeds back into something I want to say again later. So this is a diet and exercise, 2 by 2. So we have a diet that is high carbohydrate. This is the food guide pyramid with an unbalanced distribution, high protein at dinner. The other 2 don't meet it. Basically caloric restriction. They're losing weight. And over a 16-week period, they lost 11 pounds of fat. And of that, 64% of the weight loss was fat. So 36% came from lean tissue. Okay. Good news, they lost fat. Bad news, they lost a lot of lean tissue. If we add exercise to it, so let me tell you this exercise. See, these are 50-year-old women, so not necessarily gym rats. And so what we did was we had them do 7 days a week, 30 minutes walking. Supervised walking, and 2 days a week they did Nautilus resistance training and yoga for another 30 minutes. So based on that, over 16 weeks, the caloric expenditure should have been about 8 pounds of fat loss. So that's what we would predict. And what you see with the carbohydrate diet is we got 1 additional pound. We changed body composition quite a bit. They emphasized retaining muscle mass, and of the weight loss, they lost a lot more. A higher percentage of it was fat, so that's a good news, but it didn't translate into the energy loss very well. Our next group was our protein group. So this is our high protein group, balanced protein, focused on 30 grams per meal. And what you see is that after 16 weeks, these individuals lost more body fat and was just as good at body composition correction as the individuals who'd exercised for 16 weeks. And so one of the points I'm going to get to is that this meal effect on energy expenditure and fat metabolism, protein meals have almost the same effect as exercise. The mitochondrial effects are almost the same as exercise. I'll build that case for you. And then we did the protein exercise, and again I said what the amount should be is about 8 pounds of weight, and there you see it. When you combine exercise with the high protein diet, you actually get the metabolic effects that you're looking for. And you can see that the weight loss now is 90% of it was fat. And if you lose weight, fat, probably at least 5% will be lean just for the vascular system and protein that goes with the fat. So 90 to 95 is probably the best you can ever do. If leucine is important, where do we get it? So this is just a short table of where it comes from. And what you can see is all of the animal products at the top and all of the grain products at the bottom. And sort of the worst case scenario is wheat, and the best case scenario is whey. A lot of people say, well, that's not a very big spread, 7 to 10, that's not a very big spread in the sense of a diet. Is that meaningful? Well, if you're talking about a big dinner meal, it's not. We're eating too much protein anyway. But if you start thinking about small meals, breakfast, where you're trying to control the calories and you have very limited protein, what you choose makes a difference. So let me show you a study of that. So I'm going to switch to an animal study. So based from our human weight loss studies, we designed a series of animal studies to mimic those. So these are adult rats, not growing, 350 grams, so they've already established their lean body mass. And we taught them to eat 3 meals a day in exactly the same proportion that our humans ate, 20% of calories at breakfast, etc., big dinner. We fed them those meals for 3 months, every meal at the same time. And the sizes mimic the human eating patterns. We based the diet based on the food guide pyramid. So we took 45% or 54% carbs, 16% protein, US 13 to 18% proteins normal and fat. And so these diets are 100% the same. The only difference in them is that we use 4 different proteins. If you remember from the last slide, basically we used our wheat, which is about 6.8%, soy, eggs. So what we have is a curve. What we have is a range of leucine intakes. So we're basically going to use these diets, 100% the same carbs, fiber, fat, calories, same amount of protein, just different in protein, the type of protein. And we looked actually the first data I'm going to show you is after 2 weeks of feeding it. Here's the protein synthesis data. So here's after the overnight fast, and here's after the breakfast meals. So an hour later, we're measuring protein synthesis. And what we found was that there was basically no change with the wheat or soy. It wasn't enough leucine to trigger the process. And as we go on to the egg and whey, we got the response. Remember that S-shaped curve that I showed you earlier? Well, we have sort of designed this experiment to show you that. We've got a range of proteins. At that level of protein and calories, we split them. And we sort of knew the outcome at the beginning because we sort of had the number in mind. And what we had known from some other studies is we thought that to trigger it, it would take 60 milligrams of leucine in the meal. So we picked the design to make that spread. And what you see is it exactly took that number. And very little difference, 54 milligrams to 60, and we picked up the difference. And that's the key to why this is a threshold response. What difference does it really make? So there's a lot of people who've done different protein things. You can do an acute experiment. This has been fed for 2 weeks. But now let me show you when we take it on out for 3 months. So this is the sarcopenia story. So these are adult rats. They're not growing, stable lean body mass. We fed it, and after 3 months of feeding, what we see is the whey has about an 8% larger lean muscle mass. This is an individual muscle, the gastrocnemius, muscle mass than the individuals that ate the whey. 100% the same protein, 100% the same diet, just the difference in the 2 proteins. Okay? You say, well, that's not very big difference, but if you think about sarcopenia and you could generate an 8% lean body mass in 3 months, that's probably pretty significant. Even more important, though, is look what happened to the energy. That star over there represents something. Basically, here's the fat accumulation over that period. By triggering protein synthesis, which is a very energy-dependent process, what it does is burn lots of calories. And what you see here is that the wheat, 100% the same calories, deposited 3 times more body fat in the same period. That's the effect of a cereal breakfast. We then were criticized when we went to publish it and said, well, these proteins have all sorts of differences, and they're different in absorption, and they're different in other amino acids. And we said, bull. But basically what we ran was the experiment. So here's the exact same thing, our baseline, our wheat, and our whey. And what we did was we just took the wheat breakfast, and we added the difference of the leucine on top. We just sprinkled the leucine into the diet and added up to make up to the whey, and we get exactly the same result as it. It's due to leucine. 100% due to the leucine content in that triggering. Okay, I want to finish and talk a little about the energy issues that I've been alluding to. So AMP kinase is an energy signal, is an energy sensor in the body. It has lots of outcomes. It has effects on when the ATP level goes down in muscle. When AMP goes up, it senses it and it triggers a lack of energy. And it triggers things like glucose uptake. It triggers things like fatty acid oxidation through ACC, acyl-CoA carboxylase. And it also shuts down energy-dependent processes. It shuts down protein synthesis. It shuts down elongation factor 2 protein synthesis. I'm going to talk about this. So I'm going to talk about AMP kinase, mTOR, actually BP1, EIF2, and ACC. I'm going to talk about those. We talk about initiation all the time. Elongation is the process that, initiation, then you have to elongate it. This is where you make the chain. And every time you add an amino acid to the chain, it takes 3 ATPs. 1 ATP and 2 GTPs. So first charging the tRNA, then another one with the EIF2 system, and another one with the translocation factor. 3 ATPs, high energy phosphates, for every amino acid added. Some estimates are 40% of muscle energy goes for protein synthesis when it's triggered. Okay? It's a huge effect. So this is our issue of protein synthesis before. Here's our meal, our duration. One of the questions we started asking is, why does it quit? If you look at that system, it's still activated. Why did it quit? So here is that pattern, muscle protein synthesis 90, so we've got that pattern, comes back down at about 180 minutes. So there's the pattern I showed you. Why does it quit? One of the things that we know is that at 180 minutes, plasma leucine is still elevated. Insulin's back to the baseline, so that could be part of it. All the initiation factors are still elevated, but protein synthesis quit. What we've now learned is that EIF2 is becoming inactive. And so what we did is we went on and looked at that, and we looked at giving energy substrates. So here's those treatments again, carb leucine and carb plus leucine. And what we found is that if we give a supplement at about an hour and a half, 90 minutes to an hour and 20 minutes after the meal, we can extend this out to almost 5 hours just by giving a small supplement of carbs or leucine. And we looked at the initiation factors, and so here's EIF2 phosphorylation. What you see is the exact inverse, is that when it shuts down, we inhibit, we phosphorylate EIF2 and it shuts it down. If we give these energy substrates, it continues running. Here's the EIF2 again. I just moved it down there for reference. This is a fairly complicated slide in terms of the energy. So let's look at just the clear bars. The open bars is the AMP level. What you see is, so at fasted, we've got a catabolic, we're negative energy at that point. So we'll call that 100. We give a diet, phosphorylation goes, the AMP goes down, ATP goes up. And then at the end of that, what we see is a big increase in AMP levels. The muscle's running out of energy. And it triggers, in the black bar, AMP kinase. So what we do is we trigger this energy sensor to say it's out of energy. And what you notice is this effect is bigger than an overnight starvation. It's much higher, it's much more energy negative than starving for 13 hours. We then went on and looked at those energy effects, and what we find is that by giving this level of energy, we plateaued it all. We kept them all down. We don't trigger the energy. In other words, we're replacing the energy. Kind of interesting. Let's go on to another study. So what we found now is we know about this initiation part, we know about the energy cost of elongation, but what we've now discovered is that by giving leucine, we know we can trigger initiation, but by giving leucine, we can also change the energy status. If we look, I'll show on the next slide, it's a calorie issue that leucine is more effective energy source than glucose. So here's another study, same thing. Here's that 0, 90, and 180 pattern, muscle protein synthesis. So now these are the same two. So the hash lines are the same two bars, same treatments that I showed you before, but now we're going to look at two different levels. So instead of 270 milligrams of leucine, we're going to go down to 80. And instead of 2.6 grams of carbohydrate, we're going to go down to 1. And what you see is that we've still triggered it, but a little less. Okay? Not quite the same effect. Okay? And if you look at the calorie levels, what you see here is the actual calories of the supplement. It took almost tenfold more
tenfold more energy to do it with carbohydrate than it does with amino acids to get the effect. So here's the muscle protein synthesis, and we'll look at this last one. So here's the AMP kinase, and what you see is basically the effect you'd want, that basically AMP goes up, and then with the supplements goes down. But one stands out is the leucine 80. It triggers protein synthesis, but what we've got is a high AMP. And that sort of made us really think about it for a long time. And so we looked a little further, and this is sort of the data in more detail. So here's the AMP kinase. So what you see is that AMP kinase goes down after the feeding. We have lots of energy, and it goes up at 180 as it runs out. When we give leucine, basically it kept it at that fed level. And if you look at EIF2, it kept it at the fed level. Okay? We'll go on and add in the other data set now. If you look at the leucine 80 data, what you see here is that it's beginning to run out of energy. You saw on the last slide the AMP kinase actually triggered, or the AMP went up. AMP kinase has triggered, and what you see is it's beginning to show up in the elongation factor. It hasn't totally shut it down, and so what we ended up doing is catching this exactly at the transition of the signaling. And what we're learning from this is how the body's regulating energy at the mitochondrial level, and that basically protein synthesis is so energy expensive. This is the cause of thermogenic effects of diet, by the way. It's so energy expensive that the muscle will actually run out of energy, and it's protecting itself from that. And so as it shuts down, the first thing that happened is ATP ran out. It's triggering AMP. And what we did was we caught it in the transition where the elongation factor is shutting down, it's not quite done, and protein synthesis was still running. If you go to the carb one, what we see is the beginning of the transition. Basically, the minimum level, it's now about doubled. AMP kinase is beginning to sense it running out of energy. So basically, this duration of a meal and protein synthesis relates to how much energy is present. And it appears that leucine has a unique way of triggering energy metabolism in muscle. And so what we've learned from these studies is first of all, as we look at protein needs, what we now know is that protein quantity and quality really is a key. It looks like for adults, that 30-gram threshold, that 30 gram per meal is really a key aspect of supplying it. And it looks like leucine is actually a determinant of how much protein you need. And that in terms of changing American diets, the meal that is most incorrect is the breakfast composition. We're way too low at that first meal of the day. And so speculation from some of this research, one of the things that we now believe and what we've seen in our weight loss is that the thermogenic effect of protein, to actually observe it, what you need to worry about is protein distribution. It's not just about how much protein you ate per day, it's about how many meals trigger protein synthesis. And that's one of the reasons we think we've seen body compositions in our weight loss studies. And so we think that the effect is that there's a big effect on mitochondria in terms of fat oxidation. We think the reason that leucine is more effective than carbohydrates is that carbohydrates actually shut down fat oxidation, where leucine actually accelerates it. And so what you're getting is an effect of accelerating fat oxidation in muscle, and that's one of the reasons we think it's so effective in metabolic syndrome in treating abdominal obesity, is that it triggers fat oxidation. So at this point, what we would advocate is that leucine is one of those markers we can use for trying to determine how much protein is necessary. There's value that we know that there are higher levels of protein have beneficial effects, but we need a mechanism to underpin it. The mechanism, at least at this point, that looks like it's viable is the leucine level, and that gives us some indication of how much protein we need. So with that, was a lot of tidbits of information, but I appreciate your time and take any questions. Thanks. What do we recommend eating? Again, it depends on what meal. If you want to shift dinner to breakfast, that's perfectly great. If you want a 700-calorie breakfast. Most Americans are on the run, so in our weight loss studies, we
We either went with kind of a traditional sort of breakfast, sort of like an egg and a lean Canadian bacon, milk sort of thing, or we went with protein shakes and Greek yogurts and things like that. So what you want to do is get very high quality protein in limited calories for most Americans. So that's how we've done it.
So we all agree that the RDA is something, for protein in particular, is something that does not reflect what is the physiology and does not really do any favor to particularly older people because of the fact that protein distribution is so fundamental. The big problem that I see, and I think you've seen enough, is how we can make IOM change those guidelines, because I am not sure who sits in those panels and keeps saying there is no evidence after eons that, it's been 10 years now we're preaching this kind of, we've started evaluating this kind of problems. How do you do that? Because
no magic formula. We think about it a lot. I work with the egg folks, and we have major strategies in terms of how we interact with those dietary guidelines committees. But I think that the change from the food guide pyramid to a plate look emphasizing protein shows that they're at least aware of it. But what we're doing is fighting a 50-year tradition of emphasizing fat as being the root of all evil in nutrition, and that you had to stay away from cholesterol and saturated fat. And so to sort of swallow that pill and say, whoops, we got that wrong, folks, sorry, they're not really ready to jump on that. I think the saving grace to that is I believe the consumer is actually adopting it. And I think one of the things that the dietary guidelines are going to have to confront is that the health magazines, Women's Health, Women's Fitness, Men's Health, you look at them and they preach this sort of approach. I think the dietary guidelines are going to have to look at whether they're either going to become irrelevant, consumers are not going to have any interest in all and treat them as irrelevant, or whether they change. So how quickly that's going to happen, we'd like to think the next one will change some more, but I don't know if they get it, and I'm not sure they're willing to swallow the pill yet. But I think it's coming, but it's sure slow. And I think one of the problems that all of us who work in protein areas recognize is that the majority of people who work in the field of nutrition don't understand protein very well. They think amino acids are a total black box to them, and they just don't get it. And one of the things I wanted to emphasize is that what we don't want to do is play the old game. We don't want to fight the RDA. We don't want to fight nitrogen balance. What we want to do is change the playing field. So if we establish that meals are the key, and 30 grams proteins are the meals, and they have to accommodate that, that automatically moves the protein intake above the RDA. And so I think that's the battle that's winnable, the meal distribution. I don't think the RDA battle is a winnable battle, and we should set it aside and ignore it.
Any effect on the renal function with the increased protein?
What we find, and pretty much everyone has found in normal individuals, is it increases glomerular filtration rate, probably increase the size of the kidney, but as far as everybody who's looked, it actually is a beneficial thing. So the issue then becomes of people who have some form of renal damage or renal failure. At what point do you start removing solutes from the diet? Frankly, a total renal failure, that's a good idea. However, dialysis means you need more protein. But the question is, where in between, when you have some level of compromise, as far as I can look at that literature, I think it's totally up in the air. Because as soon as you take protein out of the diet for renal, the kidney will shrink in size and you'll reduce glomerular filtration rate. I don't think that's a beneficial thing. So I think that's an amazing area that is understudied that we don't have the answer. But the bottom line is people who have normal function, there is no effect no detrimental effect of protein on renal function.
Just a question on the effect of leucine on skeletal muscle bioenergetics. Have you ever just
I'm sorry, I missed the last part.
Just the effect of leucine on skeletal muscle mitochondrial function?
Oh, mitochondrial.
Have you ever just given leucine to a skin muscle fiber? Because the reason I ask is, if you give pyruvate or fatty acid to muscle. It takes a while for the mitochondria to respire.
Yeah.
But if you give it an anaplerotic intermediate, it kicks off straight away.
Yeah, that's a great point. I jumped over a few things as I was watching the clock, and you know, one of the kinds of things in animal studies you need to be very sensitive to is people who put leucine in drinking water or put it in ad libitum diets. So I emphasize this is a meal threshold thing. If you don't feed meals, if you don't watch for the triggering effect, you're not going to see the effects. Trickling it in or giving it into media, you know, clearly it will serve as a substrate. I don't know quite how to relate it to this. One of the things we have seen in long-term feeding studies, though, is we increase biomass of mitochondria. So TFAM and cytochrome C and markers of DNA and mitochondria, we'll see increases in mitochondrial biogenesis. Whether it's size or number, we don't actually know. Mike Zimmel has argued that it's a direct effect through SIRT1, PCG1 alpha. We think it's actually an indirect effect of energy expenditure triggering mitochondria to have to expand. We actually think that it's similar to endurance exercise. The more you rely on energy production and an aerobic capacity, the more mitochondria you have. That's why my point about red muscle at the beginning. I think it's more effective in red muscles. Okay, thanks.